is inspection and quality control of printed circuit boards. Now, first of all, there are a number of very useful publications out there on printed circuit boards and fabrication, and I draw your attention to a couple of books first of all, and really these are probably the best books there are out there at this moment in time. There's the Clyde Coombs Printed Circuit Board Handbook, which does cover a little bit assembly, but really it is the #1 Bible of printed circuit board manufacture, now in its 6th edition. There's also a book written by a good friend of mine, Preben Lund, which is not available anymore. You have to find it in second-hand bookshops or try online, but Quality Assessment, and this literally goes through step by step the different mechanical checks you can do on printed circuit boards, and inspection and testing. It is, or does mimic, the IPC test methods, but it's again a very, very good book, very practical, and it's probably around 20 years old, but still fundamentally a good reference. In addition, there's the Test Methods Manual, which is IPC's Bible of test methods. So it not only goes into printed circuit board fabrication, but also into testing of boards and components and assemblies, etc. So it really is the Bible of test methods. Now, each of the methods is available to download free from the IPC website, but in all honesty, you would take hours and hours and hours to download each individual test method. It's probably better buying the book. But then when a new standard comes or is updated, you can download that free of charge to update your methods manual. In addition, IPC also has IPC 600. Now, this is basically what a lot of people refer to as the pretty picture book guide, which basically gives you the reference standards for the different levels of printed circuit boards to IPC, but also it gives you some illustrations on what to look for in terms of the boards itself. So again, like IPC 610 for inspection, this is really the inspection book for bare printed circuit boards. Now, also there are lots of other documents, as you might expect, and I just illustrate a couple here specifically on surface finishes. Printed circuit board surface finishes, these are gold, copper OSP, silver, tin, nickel gold, are all covered by individual standards, and they're useful as a reference, and also they're useful if you're not perhaps as fully up to date with PCB fabrication. At least each one is broken down into simple book bits to address individual topics. So again, they're useful as a reference as well. Now, I thought it useful just to give you an understanding of the defects in terms of what the supplier sees. Now, again, when he's checking, verifying the quality of boards or designs or products he receives for fabrication, and also the defects he actually rejects at fabrication, actually at the manufacturing stage, I've broken it down into some stats here. Now, this is just a snapshot of a couple of different suppliers, but as you can see, a lot of defects are cosmetic defects, so handling defects or perhaps cosmetic defects relating to the design of the original board. And a classic example of that is legend or nomenclature. This is the numbers, the writing R26, C4, U21. And there are a lot of boards unnecessarily rejected, in my opinion, just purely for perhaps bad imaging or bad printing of some of the legend. Again, having worked in printed circuit board fabrication, there's nothing worse than throwing a board out for a number 9 where the top of the 9 is filled in with ink. It really is irrelevant, in my opinion. Anyway, if we look at a survey that I also conducted, this is the typical types of defects that are seen in fabrication and manufacture. So when the boards go from fab into assembly, what are the issues that most people see? And here we see electrical shorts and opens, solder finishes being a big slice of that pie. And one of the reasons that solder finishes tends to be quite a big percentage is there are so many choices available in industry. So again, if you've got control of your process from your fabricator, then hopefully you will have control in your assembly process. Now, a little bit of background first of all, if you're not familiar with printed circuit board manufacture. First of all, the board was, or the printed circuit board was originally credited, or the creation of the printed circuit board was credited to Paul Eisler. So he's considered the godfather or the father of printed circuit board fabrication technology. Printed circuit boards were commonly used generally after World War II, and we saw the introduction of both single-sided and plated through hole boards at that time. In the 50s and 60s, single-sided boards were used in all types of electronics. This is advanced electronics, but also in consumer electronics. Through-hole plating became more popular in the 60s and through the 60s, and that plating technology has been used pretty much ever since for most of the printed circuit boards we now use today. Multi-layer boards were coming into popularity at the end of the 60s and into the 70s, and of course we use virtually all of our products now have a percentage of multi-layers included in them. That's not true for every company, but it certainly is quite common. Now, there are basically three types of printed circuit boards that I previously mentioned. Single-sided, which basically means there is copper generally on one side of the printed circuit board. We have holes for component mounting, but we're only soldering to one side of the printed circuit board. A double-sided or plated through hole board, as it's also referred, again is the same basic construction, but the holes are metallized with copper to make a conductive path from one side of the board to the opposite side of the board. And this also allows the solder joint to form from one side of the board to the opposite side of the board. They are more expensive than single-sided boards. Typically speaking, boards are approximately 1.6 millimeters thick, and that's the norm. And then when we talk about multi-layer boards, they may well be 1.6, but they may also be much thicker than that. We can go up to 6 and maybe even 10 millimeters thick, but that's pretty uncommon. Typically 1.6, 1.8 and possibly 2.8 are common within our industry. Now here I show a section through a board, and we'll see some of these later on, but this basically shows the knee of the hole, or the edge of the pad and the plating going through the hole. And you can see different levels of plating, or different layers of plating going from the top pad through the plated through hole. And this is typical of what you might see if you were to examine a printed circuit board today. The third type of board, which I previously mentioned, is the multi-layer. And a multi-layer, as its name suggests, is layers of copper circuitry inside the printed circuit board. So we have the outside layer, that's two, both top and bottom, the inner layers, and in this example this would be referred to as a 4-layer board because it has two internal layers. Now the method of manufacture or construction can vary from supplier to supplier. Fundamentally it's pretty much the same with most suppliers. What I show you here is an SEM, or a black and white photograph in this particular case, of the inner connection. And what you're looking at solder on the right hand side. In the middle, that layer going away from the center section is the plated through hole, and then the inner layer of copper making a connection to it. Again, we'll see some other photographs like this a little bit later on, but it just shows the basic connection of the copper to the plated through hole in a normal multi-layer construction. Now what I want to do before we actually talk about checking quality, let's just step through the manufacturing process. And I'll provide some additional information when I send out a copy of these slides to give you more material to assess. So basically, for a multi-layer construction, which is the most common today, typically if you've got a mobile phone, that will be a 6-layer printed circuit board construction, so 2 outer layers and 4 inner layers. Now, a multi-layer construction consists of outer layers, and what you're looking at here is 2 outer layers with copper, and then inner layers with etched tracks to represent the inner layer. And the extra layers, which don't have any of the orange copper on them, are what we refer to as pre-preg. And this material is used to bond all the layers together to hold them together. Basically, it's the adhesive which bonds those layers together. A pre-preg is glass woven cloth impregnated with epoxy resin. Now, when you take those materials and we put them into a heated press, we put them under pressure and we raise the temperature to laminate them together. And the epoxy resin within the pre-preg material basically flows, takes up any voids, any differences in height in the copper, and bonds the package together. After this cycle, we are dealing with a solid printed circuit board, although the outer layers are all covered with copper. Now, the first step in printed circuit board manufacture typically is drilling holes. So what I've done here is I've drilled the hole that we require, and of course it's not just one hole, it's many hundreds of holes or many thousands of holes through the board to expose the inner layers if we want to connect to them. And this is done with a drilling process, and also we must make sure those surfaces of copper are desmeared. Now, what desmearing is a chemical or plasma treatment of those copper surfaces to make sure they are clean. So when we then electroplate or electrolytically plate copper or some other metallized material to the surface, but normally always copper, we make a true and reliable interconnection. Now, to do this drilling operation, the majority of holes are produced mechanically, and I show you here a series of drill bits and also some routing tools, and these are used to drill the holes we use today for assembly. And the size of hole, the depth of the hole, will obviously be defined by the printed circuit board design. Now, just a word on holes and terminology. When we look at a multi-layer board today, there are other holes or connection points within the board. Now, you wouldn't typically see this on a 4-layer board, but you may see it on a 6, 8 and multiple layer printed circuit board assembly. But this is what we call a blind via hole or a buried via hole. Buried is really the correct term. So we've got a plated through hole on an inner layer inside the board, but we have no access to it, i.e. we can't put anything into it. And this is just used as a very effective way of connecting inner layers together, but without having any impact on the tracks and pads on the outer layer. So it's a connection point with no effect on the rest of the printed circuit board assembly. That's a buried via hole, and the hole within the plating that you see is filled up during the resin flow during the pressing cycle. Now, a blind via hole is normally always on the outside of the printed circuit board, and we're drilling down to an inner layer. Now, this will normally always be filled or capped is another term. Sometimes it's the resist, the solder mask, goes over the surface on some occasions. But basically we are either drilling mechanically or we're using a laser to cut to the copper layer inside the board, as you see here. So we're going down from the outside just to one layer, and then we plate to that inner layer, which is sometimes referred to as a target pad, and that makes the interconnection from the outside to the inner layer. Now, that obviously affects the routing or the traces on the top side of the board, but it doesn't affect anywhere else inside the board. The third type of hole in a printed circuit board is a through hole via, or simply called a via hole for short. And that would normally extend all the way through the board, and we see that quite commonly used on plated through hole and multi-layer construction. The other two vias make connections but don't affect the passage all the way through the board. Just a couple of typical examples here of vias in pads. So this is a via hole, which is a blind via in a pad, and if you were going to solder to this would be bad practice to have it as you see here. Normally it would be filled. On the bottom you see an example of a filled via in pad. So basically the via is there in the pad, but it's been filled with epoxy, with copper plating, and then has been plated over. So although you can visually see it, it shouldn't have any effect on the assembly process. The top one would cause problems during reflow soldering, causing voids most commonly during the soldering operation. Now after the board is drilled, the next step is metallization and then copper plating. So the first step is to make a connection by plating, normally by electrolysis plating, so it's a chemical reaction, to the inner layers, that's the two layers of copper with inside the board, and the outer layer. So here you can see the whole of the surface of the top and bottom have got a layer of plating on, and also the plated through hole has also got a very thin layer of plating. Now if you're using electrolysis copper, that's normally about a micron thick. It's not very thick, it's just literally making an electrical connection. And what I show you here in these two photographs are a hole that I've cut in half, and you can see on the top layers of the glass cloth with inside the board that we've drilled through, and the brown material is the thin copper which is applied to the surface of the epoxy. Now if I take that same sample and shine a light through, which I've done on the bottom photograph, so I'm shining a light through the copper plating, we should be able to see dense black area with really no porosity, no holes. You can just see some small spots of light showing through, which indicates that the copper hasn't covered completely. And that's sort of like a quality control test which is conducted normally during PCB fabrication. It's called the backlight or black light test method. Now remember, all we've done so far is put some copper on, very thin layer. We've what we refer to as metallized the board. The next step is we've got to define where we want tracks and pads on the board surface before we plate up. To do that we use a photoresist, and what you see here is photoresist on the surface of the board, both sides. We're going to expose this to UV light, ultraviolet light, through a photographic artwork. So imagine the negatives that you used to see with old photography in the days of black and white, and of course colour, but in this particular case the artwork or the film work that is used is either black or clear. So anywhere that's black will not allow the UV light to penetrate through, anywhere that's clear will allow the UV light to penetrate through, and this has an impact on the photoresist. Now those areas that are not impacted by the UV light can be developed or washed away very readily, and the photograph here shows the resist layer or the photoresist layer exposing what we want to plate up. So here you can see the plated through hole and the copper pad area defined by the photoresist. So the next step is to plate up extra copper first of all, and you can see that by the brown layer on this cross-sectional drawing, and then in this particular case we also plate on tin, and tin is used as what we refer to as a resist during etching. So the first step is to remove all of the photoresist, which we do. That leaves us with the plating that we want to retain covered by tin, as you see in this cross section, and the copper that's left on the outside of the printed circuit board, which we don't want. This is normally referred to, the whole of this process is normally referred to as subtractive technology. So you're starting off with lots of copper and you're actually removing all that you don't want from the surface of the printed circuit board, as you see in this example. So I've removed all of the copper, and I would then just be left with the tracks and pads that we want to retain. Now, in normal PCB fabrication today, we would actually strip the very thin layer of tin on the printed circuit board, exposing the copper, and then we would go through solder mask application before adding on the surface finish we want. And that surface finish might be gold, copper, tin, silver, etc. So that's the normal process that we would go through. So here we see the finished printed circuit board, which would then be subjected to electrical test, mechanical testing, to make sure that it's fabricated correctly. Now, if we're making boards as single boards, then that's what you would receive. But if you're making boards which are panels or multi-panels, then this might be an illustration of what you might receive. Now, in this particular example, you've got a funny shaped board, but it's been made up to represent an oblong with breakout sections. And the reason for this is to aid assembly, because it's more difficult to assemble a funny shaped board than a board which is square or oblong. So these breakout sections are simply there to support the board during the assembly process and perhaps gives more rigidity. But designing this correctly is important to minimize stress during assembly and also stress during test and breakout of these sections. And each one of these dimensions may need to be checked as part of your quality control program. So, mechanical testing first of all. Now here you see an operator doing different types of tests, but basically, fundamentally, he's measuring the dimensions of the printed circuit board. Now, of course, when you've got confidence in a printed circuit board supplier, all of these things should be standard practice, and you would only do this normally as an auditing process, or where you perhaps have had a problem with the supplier on a couple of batches, and then you would test or check samples to see that he's improved that particular area that he's given a problem. So in the top two photographs, we're taking direct measurements of the dimensions of the printed circuit board, the thickness of the printed circuit board to make sure it's consistent, and on the bottom image the gentleman is checking the drilled holes. Now typically you don't use drill gauges like this for plated holes. You do this for drilled holes. The reason being that the tolerance might be too large for a hole which is plated and then perhaps solder leveled. The difference in tolerance might be too great. But again, it depends on what we're trying to achieve. Now, drill blanks basically are stainless steel rods which are a defined size, and they're normally supplied in a box like this, which gives them protection from the environment and rusting and corrosion. Now, another test which is quite popular is to check flatness, and again, all these test methods are defined within the books that I mentioned and the IPC standards, but the method of doing this can be done in a couple of different ways. This is the more popular method. Basically, we take a board, put it onto a flat surface, and then measure the difference in lift from one or two sides. So as you can see, the operator is holding the board in 3 positions, and then he's using the drill blanks to measure difference in height from a flat surface. You can also do the test vertically by suspending the board vertically, so there's no weight on the board, and then measuring the out of trueness of the board using some other technique. But basically, in this particular case, you're actually using the weight of the board, or you're forcing the board down onto 2 points or 3 points and then measuring the differences. So that's the sort of the common way that it's done, either in manufacture or at goods receipt. Now, in terms of plating through, now plated through hole boards, what we want from plated through hole boards is obviously reliable connection. And it's surprising that you can have copper plating which is quite thin and still give you a reliable connection. But from a manufacturing point of view, if the board plating, the thickness of the board plating is low, then it generates problems like outgassing or blowholing during the soldering process, which then leads to spitting during hand soldering or selective soldering. It also leads to voids within the joints, which don't necessarily affect the reliability, but they certainly affect the producibility, i.e. the quality standards that you're trying to meet. Now, I would recommend these days with lead-free technology to actually have a minimum of 25 microns, and typically a PCB manufacturer looks for a plating thickness of somewhere between 25 to 35 microns. He obviously wants to be on the lower side from a manufacturing cost and time perspective, but if you have 25 microns today, really you shouldn't have any problems with outgassing unless there's a problem with porosity in the holes. So my suggestion to you, 25 as an absolute minimum in manufacturing. What you're looking at here is a gentleman using an eddy current technique. So basically what we're doing is we've got a probe, it's sitting on the board in the hole, and it takes a direct measurement. Now this is an average measurement. It cannot be give you the top and bottom of the measurement in the hole. It's just giving you an average, but they are pretty accurate provided you try it in 2 or 3 different locations. Now, another couple of very useful tools which are fairly inexpensive, and I use these all the time for looking at and checking boards, is simply a normal magnifying eyeglass on the left hand side, but in it you can have a glass which has a measurement graticule. So basically it allows you to measure pads, tracks on a board very simply. Now, some people argue with me that you can't measure 2 thou. No, I wouldn't disagree, but you can certainly see the difference between 6 thou and 10 thou. And if you want to do accurate measurements, you wouldn't use this technique. But in manufacture, to see the difference in pad sizes and trying to figure out why you've got a problem, this is perfectly good for a quick check, and probably costs you about 30-40 pounds. The other technique is to look into holes, and basically this is like a kid's kaleidoscope. You put it over the plated through hole, and then you can look through the hole and see 9 images. So you're looking around the plating within the hole, and you're seeing 9 images or representations of 9 images, hence the term the kaleidoscope. And it's simply a plastic tool with a lens and an optic which allows you to do this. Again, these are about £45. If I had to choose just one of these, I would always choose the measuring tool on the left hand side, but viewing down the plated through holes for contamination, poor plating, again, is a very simple technique and easily covered by this tool. Now, if you want to do more accurate measurements, now this is again a handheld measuring tool. It's got a light on it, and this would be somewhere around 200 to 300 pounds. But again, more accurate measurement for doing checks on printed circuit board assemblies. Now, one of the other things I think it's very important to have is a camera. Now, again, you might take this for granted, but a lot of people don't have cameras or don't know how to take close-up pictures. And obviously a picture is worth 1,000 words, particularly if you're rejecting boards or commenting on the quality of boards to a supplier. And you can buy cameras very inexpensively these days online, which are perfectly adequate for this function. If you want to buy an expensive camera, then that's fine. You can do quite good photographs with a Samsung, an iPad, an iPod, all these sort of things can do fairly good photographs. But if you want to get close up and high resolution, then you need to select the right camera. Now, back to the actual board's materials themselves, I want to highlight some of the key areas which I know cause problems all the time in manufacture, so hopefully those will represent some of the issues that you face. Now, first of all, if you are using boards which are V-scored, the critical factor here is making sure the V-score, whether it's just breakouts on the edge of boards or on multiple board assemblies within a panel or a biscuit. Now the V-score should be 30, 30, 30. That's just normally what people talk about. I know it's 30, 30, 30 doesn't match up to 100% of the board thickness, but it's a 30% rule. So typically what you're seeing on the V-score on one side is a depth of 30%, on the other side 30%, and you're leaving 30% behind. Now if you want to be accurate, you're going to measure this, but if you look at it edge on, just with an eyeglass, you get a pretty good feel for the consistency. Also, the V-score should be in line. If the V-score is slightly to one side, then the force to break this out and separate it will be greater, and you are then more likely to fracture the board, the epoxy resin, the glass bundles, or in fact solder joints on the board. Now of course, if the board thickness in this area is much thinner, then during wave soldering, selective soldering, or hand soldering, then the board is going to flex because of the heat. So that's generally what you're looking for, the 30% rule. Now here I've got an example where we've got a combination of routing and scoring. Now scoring is where you see the V-score, routing is where you're shaping the board to the size you particularly want. Now you can't V-score around corners, but you can route around corners. So sometimes people will use the combination technique to get the board design that they want. So in the example I show you, you can see how a combination of routing and V-scoring has given this particular feature on the printed circuit board. Now to measure into the V-score, if that's what you want to do, you have a tool which measures into the V's, as you see in the photograph on the left hand side, but you have to have quite a large depth to it. It has to have a large mouth, if you get my meaning. So the U area, to allow the board to go into it, there might be a limitation on where you can actually measure on a printed circuit board. Here you see an operator using the tool, and he's measuring the score depths, and he would normally measure it on 4 locations, 2 either side of the board and possibly 1 somewhere in the center. That gives him confidence that the scoring is done correctly. But it's the depth of the score and also the alignment of the V to each other. Those are the 2 critical things. So here you can see a representation of a bad V-score and also a photograph where the V-score is fairly reasonably aligned, but you can see there's a difference in the depth, and you can also see there's a difference in the score shape as well, indicating that perhaps 2 tools have been used, or 1 tool that's been redressed or modified and is not really the right size anymore. Now solder resist or solder mask. We're talking about the same thing, but some engineers call it resist, some people call it mask. So solder mask is probably the most common term, but solder resist is also a common term. Now any pad which you are going to mechanically probe, you're going to solder to, would typically always have a tolerance around it. So these are what we call copper defined pads. So the copper is a size, and then the resist, the solder mask, is slightly larger than. And I've given you a dimension here of approximately 3/1000ths of an inch, and that's typical for most designers to allow a 3/1000ths of an inch resist opening around any pad that you're going to solder to or you're going to probe with a test point or flying probe or whatever. So that's typical. So you don't really want to see resist on the pads unless they've actually been defined to do that. Now, there is a term that you might hear in the industry where we refer to as resist defined pads. Now, these are used on advanced PCB assemblies sometimes, so it allows the copper to be bigger, hence more adhesion to the board, so stronger for rework, etc. And the solder mask is made smaller, and what that then does is control the shape or size of the solder joint. So the resist is in fact over the surface of the copper, but it really you have to have a good quality PCB manufacturer to accurately do this during this fabrication stage. So here's just a couple of examples of your typical printed circuit board. The resist opening. The one on the bottom shows a slight variation in mismatch, and really that's how we specify a printed circuit board. We say that we won't accept resist on the pad if that's an error, and also we want to make sure the resist is central to the pad area. If it's slightly misplaced, it really isn't a major issue, but certainly the design rule should not allow two tracks or two pads to be exposed, because a solder short could then form. Now, another critical factor which is often not specified, it should be but not specified by most designers, is solder mask thickness. Now, I just show you an example here of solder mask thickness on the surface of the board, and if the mask varies in thickness across the surface of the board, it can actually affect the printing operation, and it can actually affect other assembly processes. But it's strange that this is quite often not really well defined. But what you can see here is the resist is coating the tracks and pads, but it's not that even. Well, this is what you typically would find, and it very much depends on the fabricator, and also it depends on the type of mask used. Most liquid coatings will tend to be thin on the sharp edges, as I represent here, and much thicker on the flat surface and across the laminate surface. So it's just something to be aware of, and you'd normally specify the minimum thickness, and ideally in a surface mount application you would give an average thickness across the surface of the printed circuit board. But remember, a lot of people never ever mention it, which they should. Now, it's fairly uncommon to have solder mask lifting from the printed circuit board today. Clearly there is something wrong if resist lifts, in all honesty. But the peel test is used when you're conformally coating a board with resist on, or you're testing the adhesion of the mask to the board. And this is a fairly simple test which you can conduct yourself. Basically, you're measuring a distance, and the tape I show in the photograph here, which I'm just blowing up ever so slightly, has got marks on. So I've defined the areas I'm going to mark up, and I'm using normal adhesive tape, 3M sticky tape, to look at the adhesion. But before applying the tape to the surface of the board, I've actually scored it with a knife. So I've actually made a crosshair pattern on the surface of the resist. I've applied the tape to it, and then I've peeled it off. And then we use the criteria on the ASTM or IPC method, it's pretty much the same, on how much is removed, and that gives you a quality check on the adhesion. In all honesty, any good solder resist should not fail this test. There's something wrong in the cure, the thickness, or the adhesion underneath the mask if that is the case. Same basic test is applied to conformal coatings as well, to look at the adhesion of that to the resist surface. Now, a couple of other things which are commonly seen with resist, and this is perhaps a bit more advice because it's not defined within standards that well, and this is undercutting, and I see this a lot on modern printed circuit boards. Now, Undercutting is where the solder mask is present on the board, but during the imaging and developing stage you can see evidence that it's overhanging. So on the photograph I show a lighter area away from the resist surrounding a plated through hole, and that lighter green area on the bottom sort of area of the image, the photograph on the right hand side, is a thinner area, and I've tried to draw it in cross section on the slide so you get a feel how it's coming over the surface of the laminate. Now, how does this cause a problem? Well, it can trap flux, it can trap small bits of solder, so it can trap material underneath this overhang, and it's very difficult to clean it away. So although it may not cause a problem, it's certainly difficult to clean it away. So it's something that is bad practice really when you get it in fabrication. It's something that should be highlighted to the PCB supplier because it's clearly not right. It may not have an impact and it may not be defined in any standards. So I mention it for completeness. It's an error. It should be corrected. Now, as I said previously, the resist or the solder mask thickness is important. If it's undercut, as we just described, it can have an impact on cleaning, removal of residue solder paste, particles after printing, etc. So think about that when next you're looking at a printed circuit board. Now, the height of the resist, I've also mentioned, can have an effect on assembly. If the resist is too high above the pad surface, then printing might be a problem. If you try and print solder paste onto that pad, because the stencil is lifted off of the surface, off the pad, by the resist, then you might get poor release of the solder paste from the stencil. Now, from a soldering point of view, particularly wave soldering, the closer the resist is to the pad surface during wave soldering or selective soldering, it can actually cause the solder to be pushed away from the pad area. Remember that solder has a meniscus. If the solder can't penetrate into the copper area, then you'll get a skipped or unsoldered joint, and it's particularly common on test points. So if you're running a wave soldering or a selective soldering process and you suddenly have lots of test points that are not soldering, just check and see the thickness of the resist and see if that is having an effect. Another thing is the legend or the nomenclature. Here I've introduced a white blob to the side of the resist. Now again, a combination of thick resist and the legend would definitely have an impact on fine pitch solder paste printing. So, well, always my recommendation is not to have legend on a board in the first place, but it's a combination possibly of resist thickness and legend which could potentially have an impact on the yield from a process. So just think about resist and resist thickness, one of the things that's very commonly never ever specified on a printed circuit board assembly, which it should be, but that's life, it happens. Right, on to the plating. Now, I showed this photograph earlier on when we were talking about how a board is made, and I thought it's worth just pointing out some things for you. Now, modern plating technology does vary subtly, but this is just a typical example of a board with plating on the pad and into the hole. So I'm pointing out first of all in this area here the original copper foil. So this is the original copper foil that was on the outside of the board before we did anything, before we drilled and plated. The next two layers of copper here are the copper which has been plated through the hole to make the electrical connection from side 1 to side 2. And then the white black area here is tin lead. Now, tin lead used to be used as a etch resist to define the tracks and pads. Today it's normally just tin, because tin is easy to remove and the tin lead is not used as part of the assembly process anymore. This cross-sectional view is of a track, it could be a pad on a printed circuit board, and just to highlight the areas again, here's the copper foil, here is the plated copper, and this, in this particular case, is the tin lead. Now what we see here is undercutting, and this undercut here is defined in the IPC standards, and this is where we get track reduction. So normally in any design of a printed circuit board, the tracks will be defined in the design file or the Gerber file from the design engineer, but the actual track sizes on the board will be smaller because of the etching process. Etching of the copper does not go just straight down, it eats into the edge of the copper as well. So there is always a track reduction of a small amount every time you produce a pad or a track on a printed circuit board by subtractive technology, which is, as I said earlier, the most common method of fabrication. Now into the inner layer again, actually into the board, I'm just pointing out the inner layer connection, that's on the right hand side, which is connected to the plating. And this is what you'd expect to see if you microsectioned a board. This is what the connection point that you would see, in this particular case using an SEM, a scanning electron microscope view. Now a couple of other microsections, and what you're looking at here is a plated through hole on a printed circuit board, but also a blind via. So as we saw earlier, this is the blind via, so this is the outside of the board here and this side, and this is the blind via plated to the inner layer connection on this multi-layer construction. So let's just talk about packaging. Now packaging of printed circuit boards, when they're supplied to you, should protect the board mechanically and also should protect the board to some degree from outside effects like moisture, gaseous materials, etc. But it depends what you're prepared to pay. The more you pay, the better protection you get. So it's understanding. Now if you're going to have boards supplied to you and use them quite quickly, within 6 months or so, this type of vacuum forming is perfectly adequate. But the effect of the packaging you should bear in mind. If you've got lots of boards which have got sharp edges on, those sharp edges can cause the packaging to split and crack. So on the bottom left hand corner you can see how it's opened up. Now we don't get much protection, but remember the plastic is porous anyway, so plastic will not stop moisture ingress into the board. It will protect the board, it will give it some level of protection. If you want to guarantee the board, if it's a very expensive multi-layer, from being affected by moisture, then you need to use bags similar to the products that we use for components, not simple vacuum form or vacuum shrink wrap packaging that you see in these examples. But these are the most common that you see in industry today. The bottom right really is ridiculous. Somebody has vacuum formed some boards and they've used a silica gel, which is fine, that absorbs moisture, but the silica gel is actually got to be in the same area of the packaging as the boards, not sealed in a completely separate area of the packaging. It won't be effective at all. Now another thing to understand when in quality control and checking boards is what the actual marking on the board means. Now this may sound obvious, but trust me, I have this problem all the time. And here we see a number of different marks on the board. So you should know from your supplier what it actually means. So there will be a marking which indicates the supplier, and there should be a marking of the board reference number perhaps, but certainly there will be a marking of boards when they're made. And in these cases you've got two examples where the mark is put into the solder resist, which is one of the final manufacturing processes, so it's the end of the production process, and you've got one on the top left which is etched into the copper. Again, that's sort of like midway through the manufacturing process if it's a multi-layer board. Now if you've got boards that have got legend marking on the outside of the board, you don't really know what and when that was put on unless you understand the supplier and when he produces boards. So the point I'm making here is just understand what the date code means, when it's put on, so then you have confidence in when that date code represents and what it represents on the PCB. Don't just take it for granted that it was made last week. It may not have been. Now on surface finishes, there are lots of different surface finishes available to you. Now as part of this webinar, I'm providing a series of charts which will give you high magnification photographs of each of the different surface finishes. So again, you've got something as a point of reference. But I wanted to show you these just as a couple of examples, and here I show you silver and tin. So as you might see it on the pads, and then at high magnification layers counts. So it gives you something to check against any boards that when you receive them to see that they are of a similar quality. So here you see this second photograph, nickel gold and copper OSP. So these are typical of what to expect when you're looking at surface finishes. But a simple way of making up your own pictorial reference standards is take an example of a board from a batch that you know is working perfectly and soldering perfectly, and there you have, you've created your own reference standard. The only thing that would change may be the solderability of that finish, and depending on the type of finish it may change colour due to age. But if you were to photograph it, you've got your own reference, or you can refer to the charts that I'll be providing with this webinar. And finally, solder level boards. This is an example of solder level, and this is solder level on ultra-fine pitch. So don't just believe that you have to get rid of solder leveling when you move to fine pitch. It depends on your control and the quality of the PCB manufacturer you're using. Now just to move on to nickel gold as an example, this is one example that I see a lot of, and really it's not very well controlled process. This is nickel foot, and if you look very carefully at the pad and the photograph on the top image, you can see how there's a ghost line, a line around the edge like a smudge, and that's what we refer to as nickel foot. Now I've done a microsection on this example which you see on the bottom, and you can actually see that the plating is off of the pad and is actually plating up around the solder resist. This is just not acceptable. So again, refer to your own standards and just check your boards. If you start to see this being or coming into common or becoming common on some of your batches of boards, then speak to your supplier. If you imagine if you've reduced the area between two pads on a printed circuit boards, are you liable to get more solder shorts? I think so. Now in terms of plating and plating thicknesses, normally that's checked by microsectioning. However, some very thin finishes like silver, like gold and tin, you can't. You have to do a physical measurement, possibly with XRF. But again, talk to your PCB manufacturer. How does he check the quality and consistency? So here I've just shown an operator checking some boards, and this is just typical of an example. Now most PCB manufacturers today have this type of technique, and they can measure very, very thin layers indeed. So this is somebody checking the variation on silver finish boards, and you can see that the variation is between 0.1 and 0.2. So again, whatever the numbers that you're looking for or the tolerances within the standard, this is one technique that can be used, but you could not do microsections and detect this level A of thickness and variation. It's just not possible. And that brings me on to microsectioning. And microsectioning is a very important technique and a very useful technique in terms of inspection and quality control of PCBs. And how we do a microsection is fairly straightforward. We take a sample, we put it into an epoxy resin and cure it, and then we slowly grind the section using different levels of grit paper. So imagine wet and dry, or as a simple example, sandpaper that you might be using on wood. not the same material, please, but you get the idea. And with the paper, wet and dry paper, we're basically using finer and finer grit. As you can see on the diagram at the bottom here, we're going from perhaps 120 up to 600, 800. In fact, we normally go up to 1,000 with paper using water and slowly grinding the section, and then we go on to a polishing stage. But normally you go up to 1,000 grit to get the best finish prior to going into the next stage. We go through a polishing step, and then we go through possibly an etching process to show up the different colors of plating, the different termination, and also to overcome some of the very small smearing that might have occurred on a microsection. And microsections are used universally around the world for different surfaces, but very popular for when we're looking at PCBs. So if we're to do a microsection, the important thing is making sure it's central to the plated through hole, and this allows us to measure the plating and be consistent. If the section is done off center, what you'll actually measure is thicker than the actual. If you imagine it, you're not going in the midpoint, so you'll actually get a thicker reading. So whenever you're looking at microsections, look closely at the sample to make sure it's been prepared properly. Here are two examples, microsections of mine, and you can see that the cut is pretty much through the middle of the plated through hole. And I've put it at an angle so you can see it. So if it wasn't in the center, then we wouldn't get very accurate readings. And this allows us to measure the thickness of the copper plating all the way through selected areas, but also the quality of plating and adhesion to the base material and also to the inner layers. So the inner layers on a printed circuit board you've already seen with microsections. This is just a drawing to illustrate what we're talking about. And the key thing is making sure the copper inner layers, those copper sheets there, are making intimate contact and reliable contact with the plating. Now the quality of the microsections that are produced for you by your friendly PCB manufacturer allow you to see a number of things. Now these examples are very poor microsections. On the one on the right hand side, it looks like the example is in London fog. You can't really see it at all. So both of these sections I repolished and reproduced again, and just look at the difference in quality between the previous ones and the ones I show now. Now I wouldn't say these are perfect, but they are 100 times better than the previous ones. And the point here is that you want to be able to see any defects or any issues in the plating, or if in this particular case we've done temperature cycles, any cracks that might have occurred in the copper, which I illustrate here. The same thing can be done for blind vias and buried vias, but these blind and buried vias may be smaller than 0.2 of a millimeter. So if you're doing this sort of microsection, you've got to be skilled at doing it, because grinding through 0.2 or 0.15 is a challenge to a lot of people. Now you can examine blind vias and buried vias with X-ray as well. And these are just two examples of mine where I've done that. Now you can't really detect opens, but it gives you confidence in the quality or consistency of the copper plating. So again, X-ray can be used, but it depends on the level of equipment you've actually got. Now on this microsection I wanted to show you this, and this is an example of hole separation or through plating separation. So in the center area here you can see, as I indicate, that the copper track inside the printed circuit board has actually separated from the plated layer during the assembly and soldering operation. So clearly that's a suspect board. Now cleanliness is something that we normally want to check on printed circuit boards, and this is normally done on assemble boards, but it's also done on boards prior to assembly as well. The normal criteria for cleanliness when checking it with an ionograph is 1.5 micrograms per centimeter squared of sodium chloride solution. That's the maximum. Now normally on a printed circuit board, a bare printed circuit board, you're looking for less than 1 microgram per centimeter squared. And when you're testing cleanliness of a printed circuit board, the board is placed into a container which either has 75% alcohol, 25% water, or it has 50-50 solution, so 50% IPA, 50% demineralized water. And you're measuring the contamination coming off of the board, and then it's represented as equivalent sodium chloride solution or salt solution. That's where the terminology comes from. And that measurement is based on the area of the board or the area of the board plus the components, depending on how you're going to set up your piece of equipment. And what I show you here is typical of the squiggly lines or the graph, the results coming from this particular test. And you can see on both of these occasions, well, certainly on the one on the left, it is below, well below 0.8 on the right hand side, because we've extended the time of the test, so you can see at the minutes at the bottom of the graph it has just gone over the 0.8. Again, this probably would still fall within acceptable standards for a bare board, but again it depends on what limits you're going to be operating to. Cleanliness assessment today is quite important, particularly for boards that are going to go through a no clean process and possibly also going to be conformally coated. You don't want to start off with a board which has got high levels of contamination and then you add to it during assembly. Now another failure mode which wouldn't necessarily be detected until you actually had the failure, but it's one of the reasons why some PCB manufacturers check the cleanliness of inner layer boards. And this is CAF, or conductive anodic filamentation, or filament growth. And what I show you here is, in the green photographs, we're actually looking at the black lines which are connecting the plated through holes. And the colored photograph on the top right is basically, I'm pointing out copper formation or copper growths within the board. This is referred to as CAF. And what is happening is a conductive path is growing through the board along the glass layers or glass bundles. And this is because some plating solutions have been left inside the board or have been allowed to migrate through the board over time. Now this happens with high temperature, high humidity, high voltages, and very, very close spacings on plated through holes or vias. Not all companies suffer from this particular problem, but it's something to be aware of. This is called conductive anodic filamentation, or CAF for short, and there's a lot of investigative work has been conducted on this failure mode. Now I mentioned X-ray, and we showed a couple of X-rays earlier on, and these are just examples that I threw in just to show you how you can pick up poor plating with X-ray. These are on 0.2 vias on a 3mm thick board, and if you're not familiar with X-ray to any great degree of detail, just look on the right hand photograph on the left hand side and you can see where the plating is missing on one plated through hole. I'll illustrate it here, but that's where it's missing. So you can't measure it with X-ray, the plating thickness, but you can see whether it's there or not. And it's always nice if you have that facility in assembly, then use it for checking your PCBs. Another example where I've used X-ray to check PCBs is where we had open circuit connections on plated through holes, and I was able to detect where the copper had separated from part of the plating. And I've illustrated it here with red arrows. Now this is not easy to find. If you know you've got a failure, it's certainly easier to find it, and of course you can do this sort of investigation very inexpensively yourself before you cut the printed circuit board up. So just think about the tools you have and see how you can use them for different things. Now, most X-ray machines do allow you to measure things, and in this example I'm measuring the size of the tracks inside a multi-layer board. I'm measuring the size of the plated via. I'm measuring the open area between inner layers on a high voltage plane. So there are certain things you can do fairly inexpensively on a medium level X-ray system. So extra things you can do which are possible. Now, we mentioned solderability or wettability testing earlier on, and the one thing I would recommend to everybody is making sure that you know what method is used to check solderability with your PCB manufacturer. If you never have a problem with solderability, that's fine. But when you do have a problem and then you test your boards and then complain to the PCB manufacturer, he will just say, well, it works with my test method, and that will be difficult for you then to argue because you've never asked in the first place how he tests the boards. Now, the best method of testing boards, although it's more expensive, is the wetting balance test. This is the industry standard, but it's not the industry standard that PCB fabricators use, unfortunately. And basically what we're doing is taking a sample that I show you on the bottom image here and measuring the individual wettability or solderability of a board sample. And you do this with a globule of solder which has been fluxed, and we're measuring the actual result. So this graph shows you a typical good result on a gold board. This is a physical measurement of the wettability, and this second example graph here shows you a poor example of the same type of plating on a board. Now, I can't go into too much detail on the wetting balance today, but if you'd like further information, I can point you in the right direction. But the bottom line is this really is the best method, although more expensive, but again it's the referee method, the laboratory test. Now, if you want a very inexpensive method, there is a test dot pattern that I use again all the time. And this is a simple pattern that can be put anywhere on the printed circuit board, and when you solder paste print your board, you actually printing onto this test pattern. So every single board you ever produce has a solderability test conducted on it. Now, you don't need to do anything. You've got the result. You're not really worried about what the result is until you have a problem. But at least every board has a verification on it. And here's an example of me using the technique on a board, but also on the waste panel. And this allows me to do a test prior to production or in production if I wish. And this can be simply done. Here I've introduced a little test area onto each of the boards within the panel, and obviously in this case also onto the panel. Now, what would you expect to see? Well, the dots of paste that are printed onto this test area, as you can see here, are slowly, the gap between them is reduced. When they reflow, this is what you'd expect to see. So some of the dots have joined together and some haven't. So the number of dots that join together is a measure of your solderability or wettability. Here you see a close-up of the stencil or a section of the stencil, and also the dots, or in this particular case little square dots. Now, this is the typical type of result that you would see if you check the number of dots which haven't coalesced. So in this example, the top example, this is after one reflow operation. You can see that the number of dots that haven't coalesced, that's the figure on the left hand side of the graph, is best for tin, nickel gold is next, silver is next, and then OSP is not as good. But after one reflow operation, when you go to do a second reflow operation on the same board, look how the scoring has changed. So tin lead or tin has deteriorated much more than the previous finish, and out of those four finishes, nickel gold is probably the more stable of the four. So again, very simple, very cheap method of inspection and quality control of surface finishes, and easily introduced. Now, something that you would not normally do, but the PCB manufacturer can do, is thermal shock testing. And this gives you confidence in the reliability of your plated through holes. Now, typically we do a thermal shock with solder, or you can do a sandbath test. And a PCB manufacturer would take samples and put them into sandbath at an elevated temperature of 260, and then they would put them into water at ambient temperature and measure the resistance change over a number of cycles. And this shows up quality of copper plating and also ductility of the copper plating. Again, it's an old test, still quite a test that's performed for high-end, high reliability printed circuit boards within industry. These are the two test patterns, and basically it's just looking for resistance change between the two tracks within the sample. So you're going through the plated through hole on a number of occasions and then measuring the result. There are similar tests which are also conducted in high-end printed circuit boards in an automated method, which we don't have time to go into in this webinar this afternoon. So a couple of just examples of how the failure mode occurs, or how samples fail within this test. Again, you can see a copper microsection, and I can just illustrate here the very fine crack line on the knee of the hole. The knee of the hole and the connection of the copper to the plated through hole is where it more commonly starts to fail, because of the higher stress in those areas during thermal cycling or during the soldering or multiple soldering operations. Here again, two more of my microsections, and again hopefully you can see quite nicely the small crack which is occurring here and occurring here. This is deeper. Now, these have not caused the product to fail, but they have caused the resistance value of the copper to change. So there is a difference. The copper resistance value gives you an indication of the quality. It doesn't necessarily mean the circuit will ever fail. So it's just a method of doing process testing. But again, quite a searching test. Now, just a couple of more examples now, and this is SEM, scanning electron microscope, of nickel gold boards after removal of the gold. And this is related to a problem that the industry faced called black pad. So on the far right hand side, this is the nickel where the gold solution or the gold plating process attacked the surface. So the gold would cover this beautifully, a solder joint would reflow beautifully over the gold, absorb the gold, but then not wet properly because of the surface of the nickel. So the solder joint unfortunately visually looks perfect, but mechanically not very sound. So some people will do stripping of gold off of the surface of nickel boards to determine the thickness of the gold plating and also the quality of the nickel afterwards. And this is what we're representing here in these examples. Again, if you want additional information on this and the failure mode called black pad, we can provide that as well. This is the technique that one of my colleagues in industry use for stripping off gold from nickel boards. Now, you have to appreciate this is a cyanide solution. This is not something you do in an assembly company. It has to be done in a laboratory environment. But this is the procedure that's conducted, but I don't recommend you try it yourself. Only speak to your PCB manufacturer about this technique. So here's just a couple of examples for completeness. Here's the pads before and after stripping. And just another example, this is a high magnification view. Again, a high magnification view still further. And it allows you to look at the surface of the nickel, which is what we're trying to do, to see whether there is a problem underneath the gold. That's what it's all about. And normally this is only conducted when you actually have a problem. Perhaps it should be done earlier, but that's the way it's normally done in industry. and again even higher magnification. This is something like about 8,000 times magnification. You have to have a pretty good microscope to be able to see this level without going to a scanning electron microscope, but it gives you a feel for what can be done in a simple lab experiment. Now finally, I just wanted to talk about plated through holes and one of the assembly defects, and this is a very, very simple test you conduct yourself. If you ever have problems with outgassing, blowholing, pinholing, or solder joints spitting at you during soldering, this is something you can do yourself. So here's a plated through hole, and we've got voids in the plating, sorry, voids in the solder. And this is what it would look like after soldering. Now, in all honesty, it doesn't really affect the reliability, but some companies don't like to see it. And we can overcome it with good quality plating. So if you want to test a board, what you do is take a soldering iron and place it on the surface of the solder joint. That will cause the solder to reflow. And if there is any thin plating or poor plating in the plated through hole, what will happen is you'll get outgassing, visually seen as bubbles, and you may well see small balls being ejected from the surface of the solder. That's what typically would happen. And what you're doing is heating up the water or the moisture within the board. It's turning to steam and coming out through the plating. To test a board, you take a board, you put a small amount of oil, high temperature oil, into the plated through hole. You then apply a soldering iron to the pad surface, a number 5, number 6 bit, so 500 degrees Fahrenheit, 600 degrees Fahrenheit. You just tin the bit ever so slightly before placing it on, so it's not a dry tip, it's a slightly tin tip, and then you wait for a few seconds, and what you should see is bubbling, as I illustrate in this cross-sectional view. And if you were to look down the hole, what you would actually see is bubbling because the water vapor or steam is coming up through the oil, and that's why you can see it during this particular test. Fairly rudimentary test, but it works very, very nicely as a method of checking the quality. So if you've got bubbling, then it's an indicator that there's a problem with the plated through hole, and you need to address this with your PCB manufacturer.